And you can start.
So thank you, Tony. Thank you for the organizers. Lovely to be here virtually with all of you. So I'm going to talk about various things. The connection to mirror symmetry is through 3D mirror symmetry conjecture, which predicts roughly that 3D n equals 4 supersymmetry theories come in pairs such that the A twist of one is equivalent to the B twist of the other. These things have moduli spaces, or the two branches called the Higgs branch and the Coulomb branch. And this duality is supposed to interchange the two of them. An important source of examples, and the only one that I am familiar with, is furnished by theories of class S. So these are obtained by compactifying a six-dimensional theory depending on a group G on a Riemann surface with punctures. So it depends on the group, the complex structure of the Riemann surface, the points that are marked on it, and a bunch of data at the points, basically conjugacy classes of residues. This thing has a dual theory, which is a certain kind of quiver gauge theory, so we'll call it S-dual. The works of Braverman, Finkelberg, and Nakajima, and of Hanani on the physics side, give an explicit construction of the Coulomb branch of S-dual. So S is going to be a theory of class S. S-dual will be the quiver theory. So they give an explicit construction of the Coulomb branch of S-dual, which is the Higgs branch of S. The other branch, which would be the Coulomb of S or the Higgs of S-dual, is the base of the Hitchin fibration associated to the theory. Or rather, there's a three-dimensional story and a four-dimensional story. One of them gives you the Hitchin base, the other gives you the full Hitchin system. The three-dimensional version gives you the entire Hitchin system. So the goal of this talk is to explore some aspects of superconformal field theories of class S and the related tamely ramified meromorphic Hitchin systems. A key geometric ingredient is the construction of a family of Hitchin systems over the compactification, the Deligne-Mumford compactification of moduli space. We will explore connections to the Deligne-Simpson problem and the behavior of good, bad, and ugly theories. So I'm going to start with a very brief review of the Hitchin system. Then I'll say a few words about the physics background, so you'll all think that I know some physics, which I don't. Then the talk will start with some detailed information about the types of nilpotents that we're going to encounter. We'll take the Hitchin system, which a priori is defined on a smooth curve, and discuss what happens when you move to a singular curve. And the really important aspect for this talk is the transition, the degeneration from a smooth curve to a singular curve. So we'll talk about that in detail in this section. I'll state the main results, talk a little more about singularities, and conclude with a few open questions. And everything I'm saying is based on published and ongoing works with Aswin Balasubramanian and Jacques Dissler. So here's the quick review of the Hitchin system. It's a global version of the quotient map from Lie algebra to Timo W, where T is the Cartan and W is the Weil group. When G is GLN, this map just sends a matrix in SLN to its spectrum or unordered set of eigenvalues. So pointing T as the ordered set of eigenvalues, the Weil group permutes it, so forgets the order. Given a base curve C and a reductive group G and a line bundle L on C, the total space of all Higgs bundles is the moduli space of L-valued G Higgs bundles on the curve C. When G is GLN, this means explicitly you're looking at pairs V phi, where V is a Rankine vector bundle, and phi is an L-valued endomorphism of the vector bundle V. So that's called the Higgs field. For general groups G, you replace V by principal G bundle P over the curve, and phi is an L-valued section of the adjoint. So you have several possibilities. You can impose stability conditions, so you get a moduli space JT type, or you can not impose it and then you get a stack with not so bad behavior. The line bundle L is usually taken to be either case C, which is the case studied by Hitchin originally, or Kc twisted by D for some effective divisor D. So we'll call D the divisor of the punctures. This thing is not circulating. Okay. So the base of the Hitchin fibration is global sections over the curve of L tens of T mod W. So you can either think of T mod W as something on which C star acts, and then you're tensoring with L under C star. Or you can take L tensor T and observe that the Weil action on the Canton T makes sense uniformly. So you take global sections of the quotient and you call that the base B. A point there determines a W Galois cover called the camel cover of C. So we call that C tilde. Namely, it's the inverse image in gamma global sections of a C of L tensor T without the W. So there's a W cover between them. So the choice of a representation row of the group maps the camel cover to the total space of L, and the image is called the spectral cover. So we'll call it C tilde sub rho, depending on the representation row. So it parameterizes the spectra with eigenvalues of the matrices rho phi as your point varies over C. When rho is faithful, the camel and spectral data are basically equivalent data, so you don't have to worry which one you're using. So explicitly, the base is given by a sum of space of global sections of powers of the basic line bundle L, where R is the number of summands is the rank of the group or the algebra. The I's are the degrees of the G invariant polynomials. So for example, for GLN, the rank is N and the degrees are di is I. For SLN, the degrees are going to be 2 to N, you just drop the trace. The quotient map from G to T mod W applied to the Higgs field phi determines a family parameterized by C of L-valued points of the quotient. And this gives you the Hitchin map. It gives you a map from a Higgs bundle to a point in the base. It sends each phi or pair V phi to its camel cover or spectral cover or the family of its spectra. In the case of the canonical bundle, Hitchin proved that the total space is holomorphically symplectic, and the map to the base is Lagrangian. So you have what's called a holomorphic or algebraic integrable system. In the meromorphic case, in other words, when L is Kc twisted by an effective divisor D, this was done, the analogous result was obtained by Markman and by Botachin. They proved that the total space is Poisson, and you know exactly what the symplectic leaves are. They're going to be the inverse images of the adjoint orbits in the Lie algebra under the residue map. So you look at each of the marked points, and at those points, you're allowing the Higgs field to have a pole. You're taking the residue. That's now a well-defined element of the Lie algebra up to conjugation. So you want to take the inverse image of some orbit, some G orbit or conjugacy class in the Lie algebra. We're going to consider only the tame case, which means that D is reduced. So that means you have first order pole at the points of D. And mostly we'll be interested in the case that the conjugacy class you choose at each of the points is nilpotent. Turns out that that's not much of a loss. Okay, so here is a little bit of how the physicists think about this. So four-dimensional superconformal field theories have been subject of study for many years. Recently, this class of theories that arise from 6 dimensions became fairly prominent. The point is that you start from a 6-dimensional theory and you compactify on a curve, and then the Hitchin system on that curve plays an important role. Specifically, the Coulomb branch associated to the 4-dimensional theory can be described as the base of the Hitchin fibration or the Hitchin integrable system. The Lie algebra here probably should be taken to be of type ADE, so simply laced. And the curve is the curve of genus G with the n marked points on it. So the choice of Lie algebra parameterizes the 6-dimensional theories. And the choice of the curve determines the surface on which we compactify the theory to go down to 4 dimensions. And at the location of the end puncture, the physicists will say that we're inserting 4-dimensional defects of the theory. 4-dimensional because it's 2 less than 6. The insertion of these defects affect the behavior of the Hitchin system at these punctures, obviously. So we're working with the tame case, which means that the pole is first order. In order to get a superconformal field theory using tame defects, you actually need to require that the residue should be nilpotent element in the Lie algebra. So that's the reason that we make that restriction. And of course, what really matters is the G conjugacy class to which the element belongs. So we label the Hitchin boundary conditions by the nilpotent orbit O sub A to which the element A belongs, or the residue of phi at A. We'll sometimes call this nilpotent orbit the Hitchin orbit associated to the defect. So the reason that we're looking at this point at type AN rather than the more general types is that when G is of type A, this is all the data we need. In other cases, it turns out that you need some additional discrete data. So the issue is you need to look at the centralizer of A, call it centralizer in G of A, and take the group of its connected components, so divide it by its connected component. You get a finite group A. In type A, for SLN, this is always trivial. For other groups, there are orbits for which this group is non-trivial, and it turns out you need to choose an element in this group or a subgroup of this group in addition to the orbit. So we want to avoid these complications for now, so let's just assume that the Lie algebra is SLN. There's a lot of work of my collaborator, Jacques Dissler, and his students on Tinker Toys, and that provides very detailed information about types D and E. And we're in the process of interpreting some of these results in the geometric language of Hitchin systems, but we're not there yet. One important feature of the story is that you get a theory for every point of MGN bar, the Deligne-Mumford compactification. So you don't need to compactify on a smooth curve. You're able to do the physics on a nodal curve. And in fact, it's very important for them to go to those limits, to the boundary strata. So they have some parameter tau that goes to I infinity, so Q goes to 0. For us, that just means that we're reaching a codimension 1 boundary component of MG bar. So in basic examples, we get a gauge theory based on the group G, which is just some form of some group associated to the Lie algebra G. So the Lie algebra is the Lie algebra of the group G. But the key phenomena that we want to focus on is that there are interesting cases where the weakly coupled gauge group is a proper subgroup H, different than G. So this often corresponds to surprising physical phenomenon that certain superconformal field theories with G group are actually S-dual to a superconformal field theory, which can be described as an H gauge theory for some smaller H. And the first such example was found by Argyris and Seiberg, and this was later given class S interpretation in works of Giotto and his collaborators, and studied in detail by Dissler, etc. So we show below that the appearance of these smaller groups as weakly coupled gauge groups can be understood using the Hitchin system on nodal curves. And this gives a clear geometric picture of how the smaller gauge groups arise. We have a classification of interesting nodes in the Hitchin system. Let me skip that.
Ron, I somehow lost. Are you talking about four dimensions or 3 dimensions?
Well, so both of those are in the picture, and I'm not going to focus on that too much. If you do the Coulomb branch of the 4-dimensional theory, you get the Hitchin base. If you compactify further on the circle, so you're going to a 3-dimensional theory, you get the whole Hitchin system. So they're both in the picture.
Mm-hmm. Okay.
Okay, so let's start the talk proper. Let me tell you a little bit about the nilpotent orbits and their effect on the spiral curves. So we're still doing a smooth curve, and we're looking near one of those marked points. So we work with Hitchin system for SLN on a smooth curve C with a reduced divisor D, which is a bunch of points pk. Nilpotent orbit for SLN is specified by its Hitchin partition, or equivalently, the dual norm partition. Let me show you what those do in SL4. So let's start with the Hitchin partition. So that means when I write 4 in bracket, that means that that I have a Higgs field. It's allowed to have a first order pole. The residue is in the regular nilpotent class, meaning it has a single Jordan block of size 4. Here there'll be a Jordan block of size 3 and another one of type 1. Here there'll be 2 of size 2, and so on. If you write each of these as a Young tableau and you transpose it, you get the norm orbit. So the dual of 4 is 1 to the 4. The dual of 3, 1 is going to be 2 and 2 1s, and so on. A third way to encode the same information is by putting weights on the nodes of the Dinkin diagram. So you get a weighted Dinkin diagram. So the way you do that is you write these norm partition sizes in decreasing order. So let's say in this case, it's 2, 1, 1, and a bunch of zeros. And you take the successive differences. So 2 to 1 gives you a 1, 1 to 1 gives you a 0, 1 to 0 gives you a 1. So the weighted Dinkin diagram is 1, 0, 1. For 2 squared, you'll get 0 because you have 2 2s in a row, then a 2, and then 0, and so on. What I want to focus on is the latter part of this diagram. So I have the quadratic, cubic, and quartic invariants. And the fact that we're forcing them to sit in one of these orbits is going to force them to vanish to various orders. So if I'm putting everything in the generic or regular nilpotent orbit, I'm making all the invariants vanish, but only to first order. If I start forcing them to sit in smaller and smaller orbits, you end up with higher and higher orders of vanishing of these pluridifferentials. So let me explain how this is done. So let me just say, we're going to continue to use the Hitchin labels. Those are perfectly adequate for the case of SLN. In general, there's a map from norm orbits to Hitchin orbits, but it is not a bijection. This is a theory due to Spaltenstein and is explained in the book by Bala and Carter. The map is finite to finite, and it's closely related to the issue that I described before about the connected components of the centralizers of elements. So it turns out that the norm orbit exactly captures the right information of a Hitchin orbit together with that discrete information. Anyway, the swell curve has an equation. So it's if W is the vertical coordinate, then it's W to the n equals summation AI W to the n minus I, where AI is a I2-pole pluridifferential on the curve C. So it's a section of Kc to the I with allowed pole of some order. So let's let pi I denote the order. Alternatively, you can think of it as a section of Kc with a pole at D to the I, and then it has a 0 of order greater than or equal to chi I, where chi I is a complementary degree. Pi plus chi is I. So for a given nilpotent orbit OK inserted at the point pk, here's how you determine the order of the pole or the order of the 0. You take I wish I could write on here. You draw the Young diagram. You fill it with numbers from 1 to n. You ignore the 1 because 1 is not a degree of invariance. So you start from the 2. And you ask yourself, in what row is it? So the 2 is going to be either in the first row or in the second row. And then the 3 and the 4 and so on. Each of them sits in a particular row. So the row number containing the number I in the num diagram, filled in the standard order from left to right and then top to bottom, determines that gives you the order of the poles. So pi I k is the row number where this happens. And chi I k is just the complement, I minus pi I k. So for example, the regular nilpotent so if we're in the first row here, the num diagram is 1 to the 4th. That means it's a row of ones. So that means everything is in the first row. So that's why I get all these ones here. That says that everything is in one row. If I do the next case down, I have a 2 and a 1 squared. So the first 2 numbers are in the 1, and the last number is in the 2, in the second row, so on. So these are just row numbers in the num diagram. So even though the Hitchin diagram is more familiar, it gives us direct information about the Jordan blocks. You see that for certain questions, the num partition is more natural. Anyway, the coefficient AI, is a pluridifferential, and you can write down its degree. It's a section of a line bundle whose degree is the canonical degree plus the degree of D. It's an I-tuple differential, so multiply by I, and you subtract the orders of vanishings, all the chi I k's. Unfortunately, I didn't fix that, but this should be 2g minus 2 times 2i plus summation pi I k. So the space of all of these is a vector space, and it has some dimension bi, which is going to be bigger than or equal to the degree minus g plus 1 by Riemann-Roch. And of course, it's also bigger than or equal to 0. So we say that the system or the conformal field theory is okay if equality holds. In other words, if bi is either this or that, which is the same as saying that either H0 or H1 must vanish. They can't both be non-zero. This is somewhat of a simplification of a trichotomy that the physicists use. It started, I think, with, I forget the history, but Gayotto and Razamat and Gayotto and Witten, one in 3 dimensions, one in 4 dimensions. So they have a trichotomy into good, bad, and ugly theories. So following the cowboy tradition, we decided that since we need a notion of not bad, or in other words, good or ugly, so we call that okay as an okay chorale. So we call a theory okay if it's not bad. And that means that either H1 or H0 of each of these line bundles has to vanish. Okay. So we need to take a moment to think about what happens when you replace the smooth curve by a Gorenstein curve or a nodal curve. I think I'm in the interest of time, I'll skip that. Let me just say everything goes through pretty much as expected. So as in the smooth case, there's a Hitchin system on that, parameterizing Higgs bundles. And you just go through all the different definitions without too many changes. You get a Hitchin base, an Hitchin map, and so on. The point is that you can allow poles on a divisor D, but you need to make sure that it consists of distinct smooth points of the curve. You don't want to hit the singularities. So when the Hitchin orbits the punctures are sufficiently big, or if you have sufficiently many singular punctures, we get a node that is unrestricted. The residue can be anything in the Lie algebra. So we call such a node the standard node. When the Lie algebra is particularly small, like A1, or if the genus is bigger than or equal to 1, or if the number of punctures is large enough, then every node is standard node. But on a 4-puncture sphere, if you have a separating standard node, that means you take P1 and just break it into 2 P1s meeting transversely at a point, with 2 of the marked points on one and 2 on the other. When the Hitchin orbits are sufficiently big, it still works, but we're going to see in a minute an example where some of the Hitchin orbits are small and they result in a node that is restricted or non-standard. In other words, so think about that. What that says is you have your reducible curve. You have some punctures here and some punctures there. At the punctures, you're requiring that you're allowing singularities, but with residues only in particularly small nilpotent orbits. And magically, that forces constraints on what the field can do at a different point. That is at the node where the two curves meet. So we'll see that in a minute. But the basic issue is to understand degenerations of Hitchin systems. So consider a one-parameter family of smooth curves CT degenerating to nodal curve C0, which might be reducible or might not. So do the corresponding Hitchin systems fit together into a family? The case of immediate interest, the one that we will focus on, is the one that I just mentioned, where CT is genus 0 and it has, it breaks into a left component and a right component. Think of it as a family of hyperbolas breaking into a pair of lines, intersecting transversally at one point P. And the marked points P split into divisors on the two components, presumably of equal size. And the running example will be 2 points on each component. So the good news is that there's a very easy sufficient condition for flatness of the family. So you can construct the family and it will be flat as long as the basic line bundle K C0 twisted by D is very ample on the limiting base curve. And then you can check that the Poisson Hitchin system for the singular curve is indeed a flat limit of the Hitchin systems for the nearby smooth curves. So in particular, the same holds for each symplectic leaf. So the whole Poisson system degenerates nicely, and each of its symplectic leaves degenerates as well. And in the example, if you have a pencil of conics through 4 points in the plane, so it's a family of hyperbolas degenerating in 3 different ways to a pair of lines, the condition is simply that this line bundle KC0D has positive degree on each of the 2 components. Without the D, it has degree -1 on each component, right? It's -2 is canonical class plus 1 for the pole at the node. So it's -1 on each. So it just says that you need at least 2 marked points on each of the 2 components. Okay. So next I want to explain, in the case that the curve becomes reducible into a left component and a right component, we can partition the base B into a left piece, a center piece, and a right piece. So here's what we do. The coefficient AI of a smooth curve is a section of a line bundle Li sub t. This is on curve number t, whose degree is -2i plus summation. I think I'm doing, this is in the case where the base curve is genus 0. You have to add 2g or something in general. Let Li0 be the limiting line bundle on the reducible curve. And let Li left and Li right be its restrictions to the left and right components of C0. There's a related thing you can do, which is take the kernel of the restriction. So instead of Li left, which is the restriction, you can look at the kernel of the restriction to the right. And that is, but that turns out to be the same as Li left twisted by minus the branch of the node. So those things are easy enough to go back and forth between. Let D be the respective degrees. These again by analogous formulas to what I have up here, except that the sum on the left is now only over the points in the left part of the divisor, plus the 1 extra point, which is the node.
I have a question.
Yeah, please.
Yeah, when you were choosing the residues on the smooth curve, you said we're going to take nilpotent
Yes.
orbits. Now when you have this reducible curve, you have, like Higgs guy on one component and a Higgs guy on the other component, which each will have a residue at the node, which will have to match.
That's
Are
right.
you still insisting that residue to be in a nilpotent orbit?
No, absolutely not. So I'm
Okay.
imposing the singularity at the punctures. The node just happens. I'm not imposing anything on it. So I'm just taking it. It has a pole just because I'm looking at sections of the canonical bundle. The canonical bundle has a built-in
Right.
first order pole at the node, but I'm not imposing. The node is not a puncture. It's not a marked point. So I'm not imposing anything on it. Whatever I get, I get. It's for me to analyze rather than to impose.
Okay.
So in physics language, the eigenvalues that you get at the node are considered to be masses. By setting the masses to 0, that's where you get a superconformal field theory. But it comes with mass deformations, which are built into the story.
Okay.
Did I answer the question?
Yeah. Yeah.
Okay. Any other questions since I've stopped? Okay. So so the sum on the left is over the punctures on the left, together with the left branch of the node, and similarly on the right. Yeah. So again, the pole orders allow for arbitrary, in other words, regular nilpotents at the node P, but or for non-nilpotents at the node. So let B sub L be the subspace of B0, parameterizing those spectral curves whose coefficients vanish on the right. And vice versa, we have BR, which is a subspace where it vanishes on the left. So we have B left plus BR mapping to B0, and we take the quotient and call that BC. So we've partitioned B into a left part, a right part, and a central part. And this is going to be crucial for the rest of the talk. So let me maybe try to illustrate it. Or let me explain what's the issue here. The dimensions of the space of sections are, so BI left is going to be the maximum of DL and 0. BI right is the maximum of DR and 0. BC, the contribution from the ith degree, can be only 1 or 0. It's going to be 1 if both D left and DR are bigger than or equal to 0, and it's 0 otherwise, because that's the condition for having a right, the two things are glued to each other, so you have to have a non-zero section coming from each side. So the question is whether these numbers, which I wrote with primes, are equal to their unprimed counterparts, which are the numbers that arise as the limit from the Hitchin system on the smooth curves. So that's what I want to analyze. So we may as well generalize a little bit. Just consider a family of smooth curves C sub t degenerating to a two-component reducible rational curve C0 in a line bundle LT, which is O of D, specializing to O of D left and O of D right on the components. So we have D left plus D right equals D. What's the limit of the vector space of sections of O of D as we go through this specialization? So if DR is greater than or equal to 0, but DL is less than 0, the limit gives a proper subset of the DRs, because the fact that you have a negative degree on the left is going to impose a condition on what you get on the right. And the codimension is exactly minus DL. DL is negative, so minus DL is positive, which equals H1 by Riemann-Roch of O of DL minus 1. DL minus 1 is the other line bundle that I mentioned. That's the kernel of the restriction to the right. So you see immediately that the limiting subspace is the kernel of the coboundary map. So there's a short exact sequence, L0, restricts to the right, and the kernel is O of the left, minus 1 for vanishing at the point. You take the coboundary map, it goes from H0 of dr to H1 of dl minus 1, and the kernel of this coboundary map is the limiting subspace. So the question is simply whether the coboundary is trivial or not. There's also a way of doing this directly on C0, ignoring the limit, which will become important later, but never mind. So for the Hitchin system, the degenerating Hitchin system, we see that the limit can be a proper subspace. And this happens exactly when the line bundle Li left has higher cohomology. In other words, H1 is non-zero. And that happens when its degree is less than or equal to -2. So in the case that L naught itself has no higher cohomology, this is necessarily insufficient. Otherwise, it goes only one way. Here's the example that I promised. So consider, as usual, a reducible curve C0 breaking into left and right components. 2 points on the left, 2 points on the right. Instead of writing the nilpotent orbits, let's just say what the orders of vanishing and orders of poles are. So 1, 1, 1, if you remember. Well, this 1, 1, 1. Order of vanishing 1, 1, 1 means that on the right I have 2 regular nilpotents, while on the left I have 2 minimal nilpotents. So let's just consider that degeneration. And then the pi's are the complementary numbers. The 3 entries correspond to quadratic, cubic, and quartic differentials. So if you work on the smooth curve, the degrees for I equals 2, 3, and 4 are 0. The dimensions are therefore always 1. On the limiting nodal curve, if we just do a little calculation, you see that dl is 0, -1, -2. So this is essentially the smallest example where you can get a -2 to occur here, just by playing with the numbers. dr is positive, and here are the expected dimensions. So notice that BC is 1, 0, 0. The short exact sequence restricting from the nodal curve to its right component. Well, I just sorted out. You work out the cohomology level, the cohomology sequence, and you see that B4 on the right, or the global section, is 1, while the prediction was 0. So this is the first example where the degree is less than or equal to -2. Consequently, the naive Hitchin base is wrong. It has the wrong dimension, different than the dimension that you get from the limit. For regular nilpotent, we saw that the vanishing orders of the AI are all 1, 1, 1. And this is what we get from the BI prime. The discrepancy between these and the unprimed versions, in this case for I equals 4, means that with the right component, the orders of vanishings are 1, 1, 2, instead of the 1, 1, 1 that you expect. So that means that you're not imposing anything at the node, you're discovering that any Higgs field with residues at the 4 points, and it's allowed to have a residue at the node, will have a very particular kind of residue at the node. So if it's nilpotent, it'll have to be of Hitchin partition 3, 1 rather than the regular one. You cannot get the regular one. Okay, so I'm going to start stating our main results. But maybe this is a good point to stop and ask if there are any questions about the setup.
So from the point of view of mirror symmetry, when you degenerate your initial curve, what happens to the, say, to 3D when you have a quiver gauge theory on the other side? When you go to the boundary, when you degenerate your curve C.
Right.
So from the very beginning, the total space of Hitchin, as you said, it's mirror dual to the Higgs branch of the quiver gauge theory.
That's right.
Yeah, so when you degenerate, what happened to this statement?
I hope I'm on the right side, but I'm
Maybe
actually
it's better to postpone until the end of
in
your
10 minutes. I'm actually going to say a little bit about that.
all right.
I think that would make more sense there.
By the way, just a question on this. Do I understand that this is the S-dual theory, right? That's the one that you are calling S-check, the quiver gauge theory.
Mm-hmm.
Well, the spaces that I'm getting are the same with a flip. So this is the Coulomb branch of.
But I was just going to check,
Higgs
is
branch
the quiver gauge theory four-dimensional?
Never
No,
three dimensions. You want to get the Hitchin system. In 4 dimensions, you get the Hitchin base. In 3 dimensions, you get the Hitchin system.
Okay, but if you want to get the Hitchin base, then the quiver gauge theory is just a four-dimensional gauge theory.
That's right.
Okay.
If you just
Yeah,
want
I
to.
just want to get
And that's
the
what I'm doing in this first pass. I'm going to focus now on the bases. So from this example, we learned that in order for the Hitchin base to fit in a flat family, the naive line bundles need to be modified so as to eliminate their higher cohomology. And that's, fortunately, this turned out to be the only obstruction. So let's do it. Let C bar be the universal curve over MGN bar, the Deligne-Manford commodification. Let K run from 2 to N. Let LK be the line bundle whose fiber is KCD to the K minus combinations of the points PI with the correct orders of vanishing as specified by the nilpotents that we put at each of the points. Now, take a partition of D into S and S check. And let MS be a divisor in the Deligne-Manford. It's going to be a boundary component consisting of reducible curves of the form CS union CS dual, such that the points of S, which is part of D, go into the left, and the points of S dual go into the right. And we also we still have to specify the genera of the two components, take the genus of CS to be 0. That turns out to be the only case that contributes. So we have our own line bundle LK, which we said is potentially wrong. It's wrong in case that there's a non-trivial H1. So we modify it by subtracting from it a combination of these boundary divisors. So the divisor that I'm calling M sub S gets subtracted with coefficient that I'll call NKS, which here's an explicit formula for it. It's a maximum of 0, or K minus 1 minus summation, some combination of K and the orders of vanishing. And whatever it is, it turns out to be the same as the H1 on CS. So the curve CS is rational. So just knowing the degree suffices to determine the H1. There's no variation there. Okay, so the theorem is that the family of SLN Hitchin bases. So you take the naive LKs, you modify them, as I just explained, by subtracting boundary components, and you push them down. So now you have a bunch of sheaves on MGN bar, and the claim is that that's a vector bundle over MGN bar, and it serves as the universal Hitchin base. The proof is an exercise in gardening. We define an operation of pruning of branches. You start with a curve with singularities. You argue that non-separating singularities somehow don't matter and you can smooth them out. So you end up with a bunch of curves intersecting transversally. And then you pick the most blighted component. You assign some numerical value to it and you minimize it. You identify the most blighted component of this union, and you show that you can remove that without affecting the dimensions involved. So that's a pruning process. You remove one component at a time until you end up with a smooth curve at the end. And the argument shows that all the relevant dimensions stay constant under these operations. Okay, so that was the first result about something global living over the Mumford. Let's go back for a moment to fiberwise structure. So we just take one curve allowed to be nodal. So any point of MGN bar. So the claim is that the Higgs moduli space over it is Poisson. Its symplectic leaves are obtained by restricting the residues at each marked point to a coadjoint orbit. And the Hitchin map is weakly Lagrangian. In particular, its restriction to generic symplectic leaves is a symplectic integrable system. So it's an exact verbatim analog of the results in the smooth case. And finally, the claim is that if you move the curve, everything fits together into a flat family of Hitchin systems over MGN bar. And the Hitchin map factors that over the previous Hitchin base, the universal Hitchin base that I constructed previously. The proofs require relatively minor modifications of the corresponding proofs for the smooth case, which were done by Markman and Botochin. We follow Markman's process. And so you just modify the proofs, and then you combine that with the existence of the Hitchin base, and you have to check that the map factors. There's a new feature here that's important to point out, which is the properness of the Hitchin map. In the smooth case, we know that the Hitchin map is proper. In the singular case, it may fail. The basic problem is that the Higgs fields at the two branches of a node are required to agree in TMOW. That's the way we defined everything. But agreeing in TMOW is not enough. They may fail to be conjugate. So for example, if we're at the 0 point of TMOW, that just says that you get a nilpotent from the right and a nilpotent from the left. But the nilpotent cone has a finite number of components, and points in different components may not be, I should have said strata, not components. They're different strata, and points in different strata are not conjugate to each other. So you need to, so the natural object that wants to live there is missing. That causes the non-compactness of the fiber or the non-properness of the map. It's closely related to the existence of non-standard nodes, which also have to do with getting some limit from the right and limit from the left, which force the intersection to be in a special nilpotent conjugacy class rather than in the regular one. Anyway, we're working on a construction of a partial compactification of Higgs to which the Hitchin map extends as a proper map. The idea is to allow certain Higgs bundles on semistable curves mapping to a singular C. So the point is that you take the node of the curve and you allow it to be replaced by a chain of P1s. You can think of the nodal curve as sitting inside a smooth surface, and you successively blow up the surface and take the total transform of the curve. So it's the original curve plus some chains of P1s. The Higgs field is in a fixed conjugacy class in the interior of each P1, but at the intersections of nearby P1s at the singular points, the conjugacy class can jump. So it's easy enough to construct examples of bundles on P1 that are locally constant, except at a couple of points where they jump. And that means that by looking at bundles not on the original curve, but on this resolved curve, you can allow essentially the phenomena that we were missing of the limit from the right and the limit from the left being in the closure of each other, but not being conjugate. So this is how you supposedly fix it. I should say.
Is it related to this compactification of Telemann and Toland and Frenkel?
I think so. It's also, I think the idea goes back 30 years to Gieseker. It was used by Lucia Caporaso in some of her works. It was used by Maurizio Cornalba. It's a common idea where you construct new sheaves or bundles or whatever you need by modifying the underlying curve to something which is not stable, but only semi-stable and is stably equivalent to it. And you construct, instead of nasty objects on the downsurge curve, you construct nice objects on the resolved curve. So it's a common enough idea. And in this particular context, a similar construction has been carried out successfully by Balaji, Barak, and Nagaraj in 2013. But they only did it codimension 1. In other words, they allow only a single node, and they do it for G of type AN. So we're hoping that this will be true for all G and for the entire Deligne-Mumford compactification. At least we don't have any reason to suspect it. We have a classification theorem for non-standard nodes. So remember, the node was standard if you could get any residue you wanted at the node, and it's non-standard or restricted if it isn't. Turns out that these things are very, very special. So in an OK SLN Hitchin system, the chi-k's, so we can define them to be vanishing orders, but let's define them instead numerically. So take the NK's, which were given by some explicit formula, add 1, call that chi-k. And the claim is that these are the vanishing orders for unique nilpotent orbit in SLN. In other words, the orders that we get at the node by imposition from the smooth points exactly behave as if we impose some conjugacy class at the node. That is highly non-trivial. There's absolutely no a priori reason for this to be true. We're not sure that it is true for other groups. But we discovered this way a Hitchin orbit at the node. The greater
So
dimension.
what happened if there were no punctures to begin with? Are all systems bad?
Yeah. If you don't have, if your curve is reducible and you don't have any punctures,
yes.
By the residue theorem, the residue will be identically 0 at the branches. Maybe I'm not saying that right. You get a standard node if you have a lot of punctures. Few punctures should make it a restricted node.
Okay.
Anyway, the interesting thing is that the greater dimension of the center, BC, so we said that it consists of a sequence of 1s and 0s. Each entry for each I from 2 to n is either 1 or 0. But there are only two possible patterns. Either it's a bunch of 1s followed by a bunch of 0s, or it's an alternation, 1, 0, 1, 0, 1, 0, 1, 0, ending with a 1, and then a bunch of 0s at the end. And that tells you that the weakly coupled group is going to be either SLK in this case, or SPK in the other case. And there are some further numerical constraints on which case can arise. Couple of more main results, and I'm trying to wind this down. So let's see be a curve of genus 0 with n+1 nodes, and we allow it to degenerate. And we specify nilpotent residues, at least one of them, let's say the last one, is regular. So Carlos Simpson has a result that says that the reducible character variety for representations with that pattern is non-empty if and only if some number d is non-negative and some other number is bigger than or equal to n. So let's explain what these numbers are. A indicates one of the n+1 punctures. C sub A is the holonomic conjugacy class at that point, so it's a subgroup of SLN. It's a conjugacy class in SLN. MA is the largest multiplicity of one of its eigenvalues. And then you take the complementary number, n minus MA, you call it RA. So this condition says that the sum of the RAs is bigger than or equal to n. And this condition says that the sum of the dimensions of the conjugacy classes minus some fixed contribution should be non-negative. So Simpson shows that in this case, where at least one class is regular, you get an irreducible, you get a non-empty character variety if and only if these two conditions hold. And in that case, the number D has an interpretation. It is, the number D is the virtual dimension of the character variety. So if it's not empty, this is the dimension of the character variety. Or by non-abelian Hodge theory, that's the dimension of the Higgs moduli space. So one of our results says that in the regular case, Simpson's conditions are exactly equivalent to what we call the OK condition. In other words, the theory being not bad as applied to the line bundles LK. So in the regular case, demanding that the strongly parabolic Higgs bundle be OK is necessary and sufficient for the corresponding irreducible character variety to be non-empty. That's what Simpson tells us. By non-abelian Hodge theory, this is the same as demanding the non-emptiness of the modular space of semi-stable Higgs bundles. So the new feature here is that semi-stability in the Higgs sense admits a translation to a condition of the line bundle LK appearing in the description of the Hitchin base. So what happens if we relax the assumption that one of the residues is regular? So in that case, Simpson's two conditions are known to be necessary, but not sufficient. They're actually known not to be sufficient for the non-emptiness of the character variety. So a natural guess is that the OK condition of the line bundles, which is stronger than Simpson's condition in this case, might be sufficient. So is it sufficient to ensure non-emptiness? Is it maybe necessary and sufficient? So we don't have any evidence against either of these conjectures. We don't have a whole lot of evidence supporting them. So I'd rather pose these as questions than as conjectures. But the question is, can you use these ideas to characterize the existence of the non-emptiness of character varieties, the existence of local systems with specified monodromy conditions? Let me skip a few pages in the interest of time. And let me just finish with a few questions. So one puzzle for the physicists is that Coulomb branches of S-class theories decompose, and this is the answer to Jan's question from a few minutes ago. So the Coulomb branches of S-class theories decomposes hyperkähler quotients of products of Coulomb branches of limited components. So what's happening is you take your Riemann surface, you go to the boundary, and then you go to deeper and deeper strata in the boundary. In fact, you go all the way to a Pan's decomposition of your surface. You end up with a description of a product of, 3G minus 3 hyperkähler manifolds, one for each pair of Pans, divided by some big group action. So the group that you need to divide by is often the full gauge group, but sometimes it's a proper subgroup. And this is essentially the weakly coupled group H that we keep coming up with. So we give an algorithm for determining which is the case and what the weakly coupled gauge groups subgroup is. There's also a realization due to BFN, Nakajima et al., which, counter to the intuition of at least some physicists, is a hyperkähler quotient by the full group, even in cases where the physics intuition says that it should be a quotient just by the group H. So that seems to say that you can get the same hyperkähler object as a quotient of one thing by G and of another thing by H. And that gives all kinds of identifications of hyperkähler manifolds that seem mysterious and unexplained otherwise. So it'll be great to try to understand that. Another intriguing question is the structure of the base of the fibration on the symplectic leaf. So if you take the entire Poisson system, the base is obviously a vector space. But what is the base if you just fix one symplectic leaf, one set of conjugacy classes? So in type A, our algorithm shows that this is always a vector space. In fact, we're describing it as a sum of global sections of powers of some line bundle. In other types, a priori, you're getting just a subvariety of that. It's not at all clear that it goes surjectively onto it. And in fact, some of those relations have degrees 2 and 3. It's a nonlinear subvariety of a vector space. In all the cases that we've checked, or that Jacques has checked, it remains true. So the relations are nonlinear, but there's always a sequence of the variables so that you can solve for them one at a time and eliminate them and end up with the graph of a polynomial function on a vector subspace, so that the Hitchin base is a vector space in all known examples. In general, all that we know from the symplectic structure is that there's a flat structure on the base, but that doesn't say that it's a vector space. So I would pose that as another important open question. Third, we know how to identify the weakly coupled group H from its discrete data. So basically, we're looking at the curve. At each of the nodes, we get some sort of set of central parameters. We argue that the degrees of those exactly match the Casimirs of a uniquely defined group, and that group is H. So we're not constructing H geometrically. We're just determining it from the discrete data. So the question is, can we obtain the actual group in a geometric way using the spiral cover, spiral sheaf, things like that? Another question is to construct the proper Hitchin map of MG and bar. As I said, we're working on that, but I would not say that it's done. And of course, there's a whole bunch of questions related to the Deligne-Simpson problem that seem to be related. We can, at best, formulate conjectures about them. So, thank you very much.
Thank you. Questions?
Ron, what do you know about irregular case?
Let's just make sure we're using the same language.
Hitchin,
Regular or not standard?
no, irregular, Hitchin regular.
I'm sorry, what does that mean?
Ah, all right. You should know. You have a paper on that. with Tony and Emmanuel. Yeah, your divisor D is non-reduced. Yeah, and instead of fixing the conjugacy class, you should fix a little bit more. You should fix an orbit for the group, which is, correspond to this level structure.
Yeah. I think that's a great job for a graduate student.
I'm not sure a graduate student can do it, so it's better a question to you. So
I'm not sure I can do it either. That's why I need a graduate student.
yeah, what do you know? I mean, at this time about that?
Absolutely nothing. I mean,
all right.
Our intuition would fail because apparently the physics does require a reduced divisor D. So we don't know what to expect from the physics. But the question of compactifying the family of Hitchin systems and a lot, yeah, I mean, everything we do should be just as interesting in the wild case.
So you should kind of redo it from the very beginning. Yeah.
I think you'd have to.
All right. Thank you.
Anyone else?
I have a question.
Yeah.
So when you're talking about the Hitchin system over MG and bar, you mentioned at some point that you only get contributions for things that split into pieces where one of the pieces is genus 0. Is that correct?
I did say something like that. Let me find the page. Yeah, is this what you're asking about?
Yeah, this one. Can you explain a little? I didn't understand what's.
So there are various cases in which you can show that every node is standard. And so, for example, if you have a smooth curve of G is bigger than 0, and you degenerate that, you get yeah. I mean, just by looking at the combinatorics, having curves of positive genus tells you that you're going to be in the stable range of Riemann Roch, and you can just compute the dimensions. There's no room for anything to jump. So so this number NKS just turns out to be 0 unless one of the components is rational.
Okay, I see. I see.
So you can certainly define the loci MS in complete generality, but they're just not they're not necessary for in the correction to the naive Hitchin bundle.
Okay. And maybe something maybe related or not. There was also this question about the around the nodes, the residue turns out to not be nilpotent necessarily.
That's right.
So physically, does that mean you have the theory has a mass or?
Exactly. So my two co-authors had a paper before I joined them about mass deformations of superconformal field theories, and that's exactly what they do there. The key word there is a sheet. So if you're in a Lie algebra, you fix the dimension of orbit, or equivalently dimension of its centralizer. And you look at the union of all orbits of that fixed dimension. You connect irreducible components of that union. An irreducible component is called a sheet. And basically the study of these mass parameters amounts geometrically to the study of these sheets in Lie algebras. And they use a lot of results from Bala-Carter and Spaltenstein. And again, there are all kinds of phenomena that occur for groups other than AN that fortunately we don't have to worry about for type AN.
I see. So in the end, you get some sort of family of theories, and at some points they develop mass over MGN bar.
Right, yeah. So the mass is a parameter at the node. And as I said in answering a question of Tony's, at the node, we do not impose the conjugates class. It is whatever it comes out to be. So we can get fields that are non-nilpotent or have non-nilpotent residues there. The superconformal case is the fiber over 0, the case where the masses all vanish, which means that you do get nilpotent. So the nilpotent cone controls the conformal case.
I have a vague question, which I mean, you somehow alluded to it at the end, but you know, if you take the limit and you take the smooth locus of the, I mean, you remove the critical points of the Hitchin map from the limit. I assume this is just because it's an integrable system, this is going to be a family of semi-abelian varieties, right?
I'm sorry, what are you removing?
Just the singular points of the differential of the Hitchin map.
Okay, yeah.
Right. So can you read from, so these are some strange semi-abelian varieties that are attached to a spectral cover of the nodal curve, which sits in this dualizing sheaf. So can you read now from that semi-abelian variety the group H and the pattern that you had at the node?
Yeah, that's what I was alluding to towards the end. That's what I'm asking. I'm looking for an explicit construction for H in terms of the geometry of that. I mean, there's a description of H from the hyperkähler point of view as a group of hyperkähler automorphisms of the mod of something you get out of the moduli space. But we're looking for something purely algebraic geometric.
Mm. But there is something like the standard spectral yoga, some kind of a double coset in a Hecke algebra of a Weil group for H that somehow describes that semi-abelian variety. Is that what you expect?
I'm guessing that it's not just the semi-abelian variety, that it's that together with some other discrete data.
Uh-huh.
So yeah, I mean, the semi-abelian part is easy enough to compactify. You have a bunch of C star. So the number of the number of C star directions is exactly the number that I call the central parameter, the number of ones that I get in the center. And that's the rank of the group H. So that part I can fix by mechanical operation, just replace each C star with a P1 or something like that. And I think that's equivalent to replacing bundles by torsion-free sheaves, something like that. I think the hard part of the compactification is what is missed by that, which is the fact which arises from the fact that the nilpotent cone can have several components, and coming from the two different sides may land you in non-conjugate strata.
Mm. There was some explanation of this bubbling phenomenon that you were describing in terms of wonderful compactifications of the loop group.
Yeah, that does appear in the biology paper. We get in the non-compact direction, they get a torus, which is basically what you're talking about, and they take the wonderful compactification, which is a toric compactification corresponding to the chamber picture.
Mm.
You take the weight lattice and the chambers in it, and you take the corresponding toric variety. That's the wonderful compactification. And that's roughly what they put in there. But I think that only captures codimension one phenomena. I think when you get to more complicated geometries, there are additional features.
Mm. All right, any other questions? Well, thank you, Ron, again, and we'll stop for the day and we'll resume tomorrow morning at the same time. Thank you all.
Thank you, Tony. Okay, everybody. Bye-bye.